All right, if you're gearing up for a technical interview or maybe you're just trying to sharpen your coding skills, listen up. There is one problem you absolutely, positively need to know. Today, we're cracking the code on what might just be the most fundamental challenge in all of programming. So, what is this number one problem, this question that pops up in interviews over and over and over again? Well, it's called to-sum. And look, mastering this isn't just about acing one interview question, it's about really getting a core programming concept that's going to make you a much better problem solver all around. And here's the best part. It is not nearly as complicated as it sounds. Seriously, we're going to walk through it step by step. We'll start with a common trap that a lot of people fall into, and then we'll build our way up to a really elegant and super efficient solution. So, what exactly is the to-sum challenge? Let's break down the actual problem statement. On the surface, it's pretty straightforward. You get a list of numbers, an array, let's say it's 2, 7, 11, 15, and you're also given a target value, let's say it's 9. Your job is to find the positions, or the indices, of the two numbers in that list that add up to the target. So in our example, that would be the 2 and the 7. Simple enough, right? Okay, now the first idea that jumps into most people's heads leads to what we call the brute force approach. And I call it a trap because, well, while it technically works, it's hiding a major inefficiency. The brute force idea is exactly what it sounds like. You just try everything. You take the first number and you add it to every single other number in the list. Does it equal the target? No? Okay, you move on. You take the second number and you add it to every other number. You just keep grinding through, checking every possible combination until, hopefully, you find a pair that works. So in computer science, we have a way to measure this kind of inefficiency. It's called big O notation. The brute force method is what we call O(n squared, or O of n squared. All that really means is that the time it takes to solve the problem grows exponentially as your list gets bigger. So a list that's just twice as long will actually take 4 times as long to solve. You can see how this becomes a huge problem with large amounts of data. And this brings us to a classic trade-off in programming. You're going to see this all the time. The brute force way is really slow, but it barely uses any memory. The much faster solution we're about to explore, the one using a hash map, is lightning quick, but it uses more memory. Understanding how to balance this, time versus space, is such a critical skill. So, how do we get that speed? How do we break out of that slow O(n squared trap? Well, it's time to introduce the hero of our story, the hash map. This simple data structure is the entire key to a much faster, much smarter solution. So what the heck is a hash map? Just imagine a super-powered phone book. Instead of having to flip through every single page to find a name, you just look up the name, that's the key, and you instantly get the phone number, that's the value. For our problem, the key is a number from our list, and the value is its position. This ability to do an instant lookup is its superpower. This right here, this is the core strategy. This is the whole game. We're choosing to use a little bit of extra computer memory to build this hash map, our super fast phone book. And in exchange for that little bit of space, we get a massive boost in speed because we never have to search the whole list again. We can just do a quick lookup. Okay, theory is great, but let's get practical. How does this actually work when you're writing the code? Let's roll up our sleeves and walk through the logic step by step. Here's the entire algorithm. It's really just 4 simple steps. We only go through our list of numbers one time. For each number we see, we first calculate its complement. That's the other number we're looking for to hit our target. Then, step 2, we do that super fast check. Hey, have we already seen this complement number before? If the answer is yes, bam, we're done. We found our pair. If not, no big deal. We just add the number we're currently on to our map so we can find it later. But wait, there is one really crucial detail here. The order you do things in matters a lot. You absolutely must check for the complement before you add the current number to the map. Why? Well, think about it. If your target is 6 and you're currently looking at the number 3, if you add the 3 to your map first and then check for a partner, you'll just find the same 3 you just put in. By checking first, you guarantee you're only finding numbers you've already passed. All right, so a good solution works for the happy path, but a great solution has to be robust. It has to handle all the weird, tricky scenarios, what we call edge cases, that could trip it up. So let's see how our hash map approach stacks up. So what about duplicates, like an array with 3, 2, 3, and a target of 6? Yup,
Our solution handles that gracefully, correctly identifying the two different 3s. What about negative numbers? No problem. A target of 0? Handled. Even the smallest possible arrays? It just works. This solution is really, really solid. So there you have it. We've cracked the two-sum problem. But the real takeaway here is so much bigger than just this one challenge. This pattern, this idea of using a data structure like a hash map to trade a little bit of memory for a huge gain in speed, that's not just a trick. It's a fundamental problem-solving superpower. So the question isn't just about how you solve two-sum. It's about where you're going to use this powerful idea next.